This lesson will overview how to predict the quantities from a chemical reaction. As you recall, a chemical reaction depicts the chemical changes between the reactants on the left and the products on the right. Since we are performing quantitative calculations related to this, we need to make sure that the proper chemical reaction has coefficients so that we can proceed. A sample problem would look something like this. 25 grams of methane are burned. How much water is produced? Notice that I'm given information about one of the reactants on the left, mass, and I'm asked to predict the mass of a product on the right. We can map this out very directly using the mole map process. I'm given information about the mass of something, the methane, and I'm trying to find the mass of the water, something else. Therefore, it's a three-step process. A three-step process means that there are three sets of parentheses, starting with the units, grams of methane on the left, and ending with the units, grams of water on the right. The next part would be to add the units that would then allow me to drive where I write the numbers. Notice that the units process allows me to cancel grams. The first step, using molar mass, allows me to go from grams of the methane to the moles of methane. I have to cancel the moles of methane, and I relate that to the moles of water using the mole ratio. And then I'm back using the molar mass of the water where that cancels. I'm left with the mass of the water, the grams of the water, as the units. The next step is to add the numbers. Notice that the molar mass numbers come from the periodic table, and the middle factor, the mole ratio, comes from the coefficients themselves. So notice that the 2 in front of the water and the 1 in front of the methane are just placed directly into that relationship, into that line of work, When I enter this into my calculator, the answer is 56 grams of water. Notice that I have two significant figures in my provided information, therefore my answer should have 2. It's at this point we introduce a new terminology. If I'm using a reactant to predict a product, this calculation provides the theoretical amount that could be produced of water. That's the theoretical or expected yield. That will come into contrast later with the actual yield, which would be under sort of normal circumstances, as we don't always get 100% yield. The other assumption that's being made here is that there is enough oxygen to react all of the methane. And that's the important assumption, and that's going to be the subject of the next video. The next type of calculations to be made when considering chemical reactions has to do with the idea of limiting reactants. In the previous example, we were provided with a scenario where 25 grams of methane were burned to produce 56 grams of water. That made one important assumption. That assumed that there was plenty of oxygen to consume in order to do that. In other words, the methane was going to run out, and therefore the methane predicted the amount of water. What about a scenario where that's not necessarily true? What about a scenario where I have to worry about which reactant runs out first? And that's the subject of limiting reactants. So how do I approach a problem like this? Well, let's take the same reaction, methane burning to produce carbon dioxide and water. Given that a chemical reaction is an expression of a counted relationship and therefore a mole relationship, the simplest version to start with would be to say, what if I started out with 2 moles of methane and 2 moles of oxygen? What's different about this problem is that I'm provided with 2 kinds of information about the methane and information about the oxygen, whereas in previous problems, I was only provided information about one kind of thing. So the presumption here is one of these will run out before the other, but I don't know which one that is. So how do I approach that? One way to attack this problem would be to think of the information differently than perhaps you've seen chemical reactions. In other words, the 2 moles and 2 moles of each of the reactants are initial quantities, and therefore carbon dioxide and water also have an initial quantity of zeros. What if I keep track of the change represented by delta in that middle row and final represented by the letter F? What if I took account of how many of each were there in the initial, the change, and the final? What information could I get from that? The calculation, the mental process that has to happen is, notice that one of two scenarios will happen. Either the methane gets used up and I need twice as much oxygen, or 4 moles, or all of the oxygen gets used up and only 1 mole of methane gets consumed. In other words, I have to consider option 1 and option 2 in order to predict what's going to happen. And only one of these options is possible. It's pretty obvious based on the simple math here that I don't have 4 moles of oxygen to react all of my, I don't have 4 moles of oxygen to react all of my methane, but I do have 1 mole of methane to react all of my oxygen. Therefore, the oxygen is going to run out and I'm going to have extra methane. Notice that I've represented that here, where the oxygen column here, notice that all of the oxygen will be reacted, leaving with 0. And how do I know that? That's because the mole ratio of methane to oxygen is 1 to 2. In other words, 1 mole of methane will be reacted, leaving 1 mole of extra methane, and all of the oxygen will be reacted. If I continue this thought process, notice that I can fill out this middle row, because if 1 mole of methane is reacted right here, notice that the mole ratio is such that 1 mole of carbon dioxide would be produced, because it has the same coefficients. Just like if there's 2 moles of oxygen, I'm going to produce 2 moles of water. So at the end, I'm going to produce 1 mole of carbon dioxide, 2 moles of water. I will have used up all of my oxygen, and I will have 1 mole of methane left over. The terminology applied to this is pretty straightforward. The methane is in excess, that I often abbreviate as INXS, and the oxygen is limiting. And it's super important to realize that it's the limiting reactant that predicts the product. The whole goal of this limiting reactant set of calculations is to determine which of the 2 reactants is limiting, because it's the limiting reactant that predicts the products. The x-axis is going to be left over. It's like those leftover eggs when you're making cookies, or the leftover flour when you're baking a cake. That doesn't predict anything. What predicts the product is what's limiting, and there's a series of calculations to make that happen. As a final thought here, if I were to visually represent what was present before and after, notice that before I have only methane and oxygen. After the reaction, I have methane, carbon dioxide, and water. In other words, it's difficult just by looking and comparing these 2 boxes to tell what's the reactant, what's the product, because I have to deal with this idea of limiting and excess, because something's going to be left over. The more specific calculations and how to do this in a more detailed manner follow in the next video. Now that we have the basics for predicting products and using balanced chemical reactions for comparing quantitative amounts, and the idea of limiting reactants, let's take a more typical scenario. Given that reactant amounts are usually measured in mass, we can't directly measure moles, so these problems start with provided information as mass. So for example, suppose the same reaction that we've used in the previous video, the burning of methane, starts with 25 grams of methane and 25 grams of oxygen. Notice that if I want to compare those 2, I can't compare it using mass, and therefore the previous thought process that I suggested and modeled doesn't work, because you can't compare using masses, you can only compare using moles. So I'm going to show you how to lay out this problem using moles and then make a decision based on how to predict the result. Since all relationships in chemistry involving chemical reactions and formulas involve moles, the first step is then logically is to say, well, I'm provided mass information, I should convert that to moles. So notice that the 25 grams of methane here can be calculated as 1.56 moles of methane, and then the 25 grams of oxygen is provided as 0.781 moles of the same. The terminology I'd like to suggest here is that these two quantities are what we have. In other words, this is what we start with. And that's just the first step in order to make the next decision, is which one is going to run out first. Well, I can't tell by inspection, just by looking at these numbers, because they're not nice and round and coefficients and so forth. So I'm just going to use a simple mole ratio to then determine how much of the other reactant. In other words, I'm going to do a mole ratio to compare oxygen to methane and methane to oxygen. So what I've done here is I've taken the moles of methane that I have, which is the 25 grams, and then I'm using a mole ratio, and I'm calculating a number of moles of oxygen that would fully react, moles of oxygen that fully react all of the methane. In other words, 1.56 moles of methane needs 3.12 moles of oxygen to fully react. On the other hand, 0.781 moles of oxygen, if it were to fully react, requires 0.391 moles of methane. Only one of these two can fully react. The other one will be in excess. So which scenario will happen? Will all of the methane react, or will all of the oxygen react? I'm going to refer to these numbers that we just calculated as what I need. So, in order to react all of the oxygen, I need 0.391 moles of methane. I only have, or I have 1.56 moles of methane. Do I have enough moles of methane to react all my oxygen? And the answer is yes, I do. On the other hand, in order to react all of my oxygen, in order to react all of my methane, I need 3.12 moles of oxygen. And notice that I don't have enough. In other words, it looks as though I can react all of my oxygen because I have enough methane to go with it, whereas I don't have enough methane to react because I don't have enough oxygen. Therefore, oxygen is limiting. Now that I know that my oxygen is limiting, notice that I can use that number to then predict the amount of water. And this is a simple two-step mole map problem where I'm going from the moles of something to the mass of the other. So again, in this region right here, I determined what I have of each of the moles. I then determined how much I need of the other to fully react each of those. Only one of them will run out, and by comparison, notice that I do not have enough oxygen. I do not have enough oxygen to react all of my methane, but I do have enough methane to react all of my oxygen, therefore the oxygen runs out. That makes it limiting. Notice that I can then use that number to predict the result, because that's what I mean by limiting reactants. That's how I have to go to prove how much result I get. Let's summarize what happened. Let's summarize the calculations from the previous example. We were provided with 25 grams of each reactant, which is 1.56 moles of methane and 0.781 moles of oxygen. Using the previous chart, we then would show that there are no amounts of the carbon dioxide and water present before the reaction initially. Taking the quantities from the previous slide, notice that we determined that we only need 0.391 moles of methane to react all of our oxygen, because the oxygen will be used up. Notice that these two numbers, the 0.391 and 0.781, match the 2-to-1 mole ratio present up here. In other words, that makes sense to me visually, even without using my calculator. These columns here are going to add or subtract, as you see, because that number is negative. Notice that I have none of the oxygen left over because it's all used up. And then I said 1.56 moles, subtracting the 0.391 that are used, means that I have excess methane in the amount of 1.17 moles. The next part would be, how do I fill out this over here? Notice that given that this table is strictly moles, I can just use mole ratios to determine the amounts that go into those cells. As we've seen before in class, if I want to relate the moles of something to the moles of something else, notice that I'm going to take my limiting reactant here, I'm going to use that up, and I'm going to use that to predict both the moles of CO2, which is going to go right there, and the moles of water, which is going to go right there. And I can just enter those quantities right there. Notice that I'm producing 0.781 moles of water, and I can see that based on that mole relationship right there. As a final note to these calculations, given that this table is in moles, and moles only, many times I'm asked for the amount of excess, or the amount in grams of the product. So I took as an example, notice that this 1.17 represents the moles of excess methane, and I can do a simple moles to mass calculations, and I determined that of the 25 grams initially present in this problem, 18.8 grams of methane are left over. I could perform a similar calculation with either the carbon dioxide or the water and determine the mass of the product. As you know, rarely do we just calculate the moles of a product or the moles of excess. We want to determine the mass.